Okay, it's a great pleasure to have the second talk of this morning session. And the speaker will be Professor Serge Rosenblum from the Weizmann Institute, and he's going to tell us about quantum error correction. This will be the first of 3 lectures.
Thank you, Ganpathy, and welcome everyone to this first lecture of a 4-lecture session. You're going to spend a long time with me, and I hope you'll appreciate it. I'd like to start maybe with like a light-hearted poll. So I assume many of you know, at least from popular literature about quantum computing, and you've all heard that one of the big aims is to factor large prime numbers. Sorry, not large prime numbers, large numbers into primes. And I'd like to ask you, in order to beat a classical machine, for example, if you have a 2000-bit number, which could never be factored by a supercomputer, how many qubits would it take in order to apply Shor's algorithm to these to this big number? And I'll remind you that today the biggest quantum computers have about 100 or a few hundred qubits. So option number 1 is about 20,000 qubits. Option number 2, 200,000. 3, 2 million. 20 million or 200 million. No, so I want to factor a 2000-bit number, and I'm asking, in order to apply Shor's algorithm, you need a quantum computer, but how many quantum bits do you need in your quantum computer? Okay, so everyone has to vote at least once. How many say you need 20,000 quantum bits in your computer? Okay, we have a few people here. How many say 200,000? Small minority. 2 million? 20 million? And 200 million? Okay, I think we have a uniform distribution here. In any case, the correct answer, as far as we know today, it could go down in the future, is about 20 million. So we have about 5 in your quantum computer to factor a number that would not be factorizable by a supercomputer. So we have 5 orders of, yeah, and it won't change so much because a classical supercomputer, yes. So we have about 5 orders of magnitude to go. And the reason we need so many qubits, even though the number of logical qubits that you need is about 14,000. So you need 14K logical qubits. And this huge gap comes because every logical qubit has to be made out of about 1,000 physical qubits. And that's because of quantum error correction. The best constructions for executing Shor's algorithm require 1,000 physical bits that are noisy, full of errors. Together, they make one logical qubit that has a very high quality. And if you take 14,000 of those, then you can factor a 2,000-bit number. This is according to constructions that we have today. I will talk about other constructions in the 4th lecture, so bear with me. QEC stands for quantum error correction. So we have a problem here. It's going to take a while. In the meantime, a lot of people are working on what's called NISQ. NISQ stands for near-term, sorry, not near-term, noisy intermediate scale quantum. So people are looking for algorithms that would be useful while we don't have this kind of error correction yet. This was coined by Preskill a few years ago. As Vijay mentioned a few days ago, the prospects of NISQ are a little bit grim we don't know of anything very useful to do with algorithms, with quantum computers, while we don't have error correction. But people are looking for it, and there could be some surprises here. No, people are, yeah, so physics problems are already done, and they provide very interesting insights, but there isn't anything that would be of interest to non-physicists, let alone that would be industrially interesting, that could be done with today's quantum computers. So a NISQ algorithm would hopefully be of interest to people outside of our community. All right, just a few words about myself. My name is Serge Rosenblum. I'm a professor at the Weizmann Institute, and I'm an experimentalist working on superconducting quantum circuits, a bit like Vijay. As someone said in the audience, they invited an experimentalist to talk about quantum error correction. I hope I won't disappoint you, but I think I might give you some very useful insights from a different direction. And interrupt me at any time with questions, mostly from the back. If there are only questions from this row, I will be slightly disappointed, so feel free. And another reason why quantum error correction is so interesting, in my opinion, is not only because it's crucial for realizing the full potential of quantum computing, but it also connects to such a wide variety of other fields. Condensed matter physics, which is why we're all here. In some sense, the previous lecture by Eduardo was, he might not agree with me, but it was somehow about quantum error correction as well. So there are very deep parallels between those fields. Don't ask me about this, but there are deep relationships to quantum gravity as well. Excuse me? I didn't know that. No, that not this. Your lecture ended here. Good. Then, of course, computer science, but not in the sense of algorithms necessarily. There are very deep relationships between quantum complexity theory and quantum error correction, and these arrows go both ways. So, from insights in quantum error correction, people have proved things about fundamental computer science. And a bit more in the applied sense, people have proposed ideas to improve metrology and sensing using quantum error correcting codes. And maybe one of you can think of another parallel, but I think it's already clear that we're talking about something very interdisciplinary here. What am I going to talk about in this 4-lecture series? Today's lecture will be a bit of a warm-up, some preliminaries, then the basics of quantum error correction, and we're going to give some examples of small codes, so small quantum error correcting codes. I hope I'm writing big enough for everyone. In lecture 2, we'll go to something a bit more formal, structured. We'll talk about stabilizer codes, which is one of the workhorses of quantum error correction. We'll talk about the surface code and topological codes, to which we had a wonderful intro today. And I'll talk about a little bit about the threshold theorem for quantum computing, for fault-tolerant quantum computing. Lecture 3, I'll talk about the future of quantum error correction. Could we do something that is a bit better than this 1/1000 overhead? And there's a lot of excitement in the past year or 2 years in this field. Mainly when it comes to QLDPC codes. to know what this acronym stands for, you have to come to lecture number 3. And in lecture 4, I might have to deal with some overflow, but I hope to get to technologies, comparing platforms. It's probably wise for me to ask this to not be recorded because I might get lynched. I start comparing technologies. And by popular demand, I will talk about one algorithm, which is Grover's algorithm, to search from an unstructured database. And some final remarks. Good. So just the outline gave me the whole blackboard. That doesn't bode well. Good. Any questions before I start? I haven't yet said anything. Let's start with some preliminaries. And before we start correcting errors, we first have to understand errors. Prabha gave a nice introduction about this, so I won't talk about it too much, but I still think it's important. Understanding errors. And usually when we talk about errors, we talk about decoherence. So what is decoherence? Anyone from the audience care to give a 5-word description of what decoherence means? I'm a very patient person. Yes, it's true. This is maybe the importance of decoherence, but what is a physical mechanism that causes decoherence of some quantum state? Exactly. So it's getting entangled with the environment, the environment stealing information that it's not supposed to have. And then our pure quantum states decohere. Let's suppose you have a quantum state, your system is described by the density matrix rho. You apply some unitary to it, but unfortunately, the unitary also sometimes involves other degrees of freedom, the environment, which we don't control. And this is going in general to cause entanglement between the environment and your system. And you can think about the environment being exceptionally evil and even measuring what comes out after this unitary. So it gets outcome K. Just to be clear, this is the environment. And then what comes out of here will be this piece here. So E rho, EK rho, EK dagger. And EK is what we call errors or error operators. Sometimes it's called the Krauss operator. I'll mention in a second. So EK, if you do the small calculation, you get that it's equal to this. So phi naught E is the initial state of the environment. And this is called an error operator. Sometimes it's called a Krauss operator. I know there was an Indian scientist that should be here. I learned this from Prabha. EK. KE, I will try. Yes, I will try to be a bit, to write clearer. Krauss operator, it's sometimes called an operation element, but really mean the same thing. And any, or almost any kind of map of a density matrix can be written in what's called the operator sum representation. Yes, it's an operator. Why is it an operator? It looks like a number, but look, U is an operator acting on the system and the environment, but you're only sandwiching it in the environment. So you stay with an operator on the system. Okay? It's not a unitary operator necessarily. It's not a Hermitian operator necessarily. And the fact that it's broader than this, right? Yes. Yes. So the operator sum representation, and I'll get to that immediately. Suppose you have some channel, some process acting on a density matrix. You can write it as the reduced, the partial trace over the environment. You're tracing out the environment. U rho cross rho E. So rho E is the density matrix of this thing. Times U dagger. And this equals sigma K EK rho EK dagger. So what is the interpretation here? What's the intuition? The intuition is that a process like epsilon, it can be an error process, a noise process, it can be a unitary that you want to apply. It can be a measurement. Any map to a density matrix can be written in such a way as a sum over these EK rho EK dagger. What is the intuition here? The intuition is that if the environment measures the outcome K of its side, then effectively the operator EK is applied to your density matrix. Because you don't have access to the measurement result of the environment, you have a sum over different EKs. And we'll see a few examples of this, which should become clear. Any questions from above? Correct. Yes. This picture.
Yeah, in the first picture, the logic gate picture. So there is a state that comes into, and there is an unitary operation happening there. And with that, there is wave function corresponds to the environment.
Yes.
So what is happening there in the, right-hand side below?
First of all, it doesn't really matter what the environment does after it interacts with us. It's the environment's business, but you can interpret it as the environment measuring what comes out of his wire, and this measurement will then collapse the state of the system onto this. If you don't know what the measurement outcome is, you have a sum, you have a probabilistic, a classical sum over these different options responding to each measurement outcome.
Okay, so so the sum is on K.
The sum is over K, yes.
Okay, so K, what is K?
My H is a K. I don't have H's in my talk, they're all Ks.
Okay. So what is K? I mean, you wrote something corresponds to K, E, kit, right? In the above.
For example, the environment can measure, is my qubit in 0 or in 1? Okay, and K would be 0 or 1.
Okay.
The environment has more qubits. It can measure in some different bases. It can do whatever it wants. But you can always label the possible measurement outcomes. This is an interpretation of this thing. You don't have to look at this picture.
Okay.
You can even ask yourself, what is the most general map, linear map, that you can apply to a density matrix that preserves the trace of the density matrix and that keeps it positive, because a density matrix has only positive eigenvalues. These are the probabilities. And you get this. So you don't have to go through this interpretation, but it makes it more intuitive.
Okay.
So it's called a CPTP map. Sorry, U is unitary. Yes, the map is linear, but it's not a unitary map.
So U, does it describe on this, yeah. So U describes the dynamics generated by the system, or is it the complete dynamics of the environment as well?
In any evolution, if you go to a bigger and bigger space, you can describe it as unitary. Okay, if you include all degrees of freedom, then you can always write evolution as unitary. Okay? So it's a unitary operation over the environment plus the system. You can always write this down in this way. This is without loss of generality. If this wasn't a unitary operator, you could increase it, include more environments, and then it would be unitary. Okay, let's move on, and I will give a few examples, so this will become clear very soon, I hope. Now, these EKs, they are very general. They don't have to be Hermitian or unitary, as I said, but you can always decompose it into a basis. And it turns out that the Pauli basis is a legitimate basis of any 2x2 matrix, or for more qubits, 2 to the n times 2 to the n. So we can always decompose K equals and these are just coefficients, so EI, K, EXK, EYK, and EZK. When someone thinks about quantum error correction, they don't ask themselves, what is the precise error or Krauss operator that happens in my system? They usually decompose it into Paulis, and they correct the Paulis. So if you can correct X, Y, and Z, you can correct any type of error. This is called error digitization. Again, this is not a proof or anything. This is an intuitive picture of why this is the case. You can, of course, formally prove that if you can correct these Paulis, you can correct any type of error. And the goal of quantum error correction is to identify which one of these operations happened, which one of these Paulis occurred, and then correct it by applying this Pauli again. We'll talk about this much more in detail. Questions about error digitization? Yes. Yes, this is for 1 qubit, but it generalizes to many qubits. We will talk about the Pauli group, which is a multiplication of Paulis or a tensor product of Paulis, and this will still hold.
So if one of these occur, then you can multiply it again and get rid of it. But if you have like both of like say X and Z together, then
Yes.
how do you get rid of it?
As we will see, one of the beautiful things about quantum error correction is that we use decoherence to fight decoherence. If you have a superposition of X and Z, for example, your error is I plus Z, or actually cos theta I plus sine theta Z. I kind of botched this. This is cos theta I plus sine theta Z. This is a theta rotation around the Z axis of your Bloch sphere. It's a unitary operator. But what you do in quantum error correction is you collapse yourself. You measure the system and you ask, was there an I, was there an X, was there a Y, or was there a Z? You break any such coherent superpositions, and then it doesn't matter where you started from. Did that answer your question?
Partially, but I'll probably it will be clear.
Okay. Yes.
So you mentioned that it need not be even Hermitian. So then if it is non-Hermitian, one brings it to a Hermitian form and then expands in Pauli this thing, or how does it work out?
These coefficients do not have to be real. They can be complex.
I see. Okay.
Okay. I presume many of you know this, but I'll write it down anyways because it's important for the rest of the talks. I'll introduce a poly group. So in quantum computing, usually we don't work with sigmas. We write x, y, and z, as you saw. X is sigma x. So it this way. Z is sigma z. And y, confusingly, is I sigma y. It's to keep everything real. Yeah, it's a decision I made in the beginning of the writing the notes, and I came to regret it very quickly. But so x is this operator, z is this operator, and y is this nice and real operator. And this equals z times x. When we think about y, I will almost never talk about y because it's just a z operator, an x operator followed by a z operator. Intuitively, what x does, it exchanges 0 and 1. It's a bit flip. Z exchanges 1 with -1, so it adds a phase only to 1. And y, well, y is both at the same time. It's a bit flip and a phase flip. We can define the n-qubit poly group, generalization to as many qubits as you like. And we write Pn, this is the group, is plus minus I, X, Y, Z, tensor product to the n. And a very useful fact that you use over and over and over again is that all poly operators, every element of this group, either commutes or anti-commutes. Let's give a few examples. So X tensor product yi, this operates on the first qubit, this operates on the second qubit, and Zx. Does it commute? Does this poly commute with this poly or anti-commute? I tried very hard to get rid of this I. Yes, you could have some I to the k here, but for the rest, it doesn't really matter for my talk. So you can quote me on this, I equals +1, and it will, oh, I see a lot of very angry faces. Okay, let me erase it. I can omit all the I's, it doesn't matter for all purposes in my talk. Do these two operators commute or anti-commute? Who votes commute? Who says anti-commute? Okay, yes, indeed, they anti-commute. Why? Well, X anti-commutes with Z, and I and X, of course, commute. So in total, it anti-commutes. Anti-commute. What about X, Y, Z? I'm going to omit the tensor products from now on because it's a bit tedious. And Y, Z, Z. Who says commute? Everyone has to raise their hands at least once. This is the rule. And okay, did I say commute or anti-commute? And who says anti-commute? Okay, they commute. They commute because, well, Z commutes with Z, X anti-commutes with Y, and Y anti-commutes with Z. If you have two polys that anti-commute, together they will commute. You can just try it out. And finally, XII, XXX, and XXIIIX. Who says anti-commute? No one? Okay, I think you got the idea. X and X commute, so we're good. All right. This summarizes the preliminary information here, so we'll get to some physics now. Okay, let's talk about error channels. There's a question. Yes.
You said that in general, E could be complex. So are there conditions on E, like when it wants to correspond to a cross operator?
The only condition, and I didn't write that down, is because you want the total probability of something happening to be 1, you'll have here, let's write this here. The probability of measuring K, of getting the outcome K, it's the trace of, just make sure I'm not botching this, trace of EK rho EK dagger. And so to conserve probability, you want that sum over EK dagger, EK is the identity operator. If this is true, they will sum to 1, and this is the only condition.
So like how does it translate to a condition on E? So here.
I don't know, you just have to,
Okay.
I'm not sure.
Okay,
It translates
thanks.
to E. No, this is a number. So you want to trace over system and environment. Actually, this does not have any environment degrees of freedom. So it's already been traced out. So it's system. Yeah. So the state, given that you measured K, is EK rho EK dagger. And the probability of this is just a trace of that thing. Okay. We'll learn about a few very important error channels. So error channels are different types of epsilon, or different types of sets of cross operators. Know thy enemy. You have to really understand the errors before you fight them. And the most famous one is the bit flip channel, where rho goes to, under the channel, 1 minus P, Ex, if you like, rho, or I rho I, let's write it explicitly, plus P, X rho X. So what are the cross operators here? I and X. You need square root 1 of P here, and E1. These are the two cross operator of the bit flip channel. You can check that this trace preserving condition holds. What does this do to the block sphere? Who is familiar with the block sphere representation here? Okay, most everyone. Start with the block sphere. This is the z-axis, x-axis, and y-axis. And under this bit flip channel, it turns into a cigar. Why a cigar? Because, for example, an eigenstate of x will not be harmed by this bit flip channel. It's only eigenstates of z and y that get affected. Is this clear? Any questions? Good. And then we have its cousin, the phase flip channel. Just have to rotate your head by 90 degrees. You get the phase flip channel. It's just the same, but you have, just writing down for completeness, 0Z. In the block sphere picture, what will happen is it will become a cigar, but now across the Z direction. This is also called the dephasing channel. The reason is simple, because this is a channel that removes any phase or any coherence of a quantum superposition state. If you start with the state 0 plus 1, this is the X state. Well, its density matrix is 1, 1, 1, 1. And under this channel, it becomes, you can just do the simple math here, and you get that it becomes 1, 1 minus 2pz, 1 minus 2pz, 1. You see that it reduces the off-diagonal elements. And for pz equals 1/2, you just have a classical superposition of 0 and 1, which would just be a line along the z-axis. Yes, correct. If you start in 1 and you apply phase flips, nothing will happen. You get the global phase, but this is not of interest. Yes. Okay. I can tell that you're a theorist because you put the 1 at the bottom. So experimentalists always put the 1 at the top because it then decays to a lower energy state. So if you permit me, I'll go this way. So the channel you're describing was actually the channel that Prabha was talking about in her talk. It's called the amplitude damping channel. And the amplitude damping channel, what it does, it turns a Bloch sphere into something like this. It shrinks the Bloch sphere slowly to the ground state. And the cross operators are interesting here. Wish I had my notes on this. So you have, any. The Bloch sphere, you can draw a map as a mapping of the Bloch sphere to some other manifold. So you go from a big sphere to a small sphere on the ground state. I'm just going to grab notes because I have something on the amplitude damping. I don't want to botch it. Oh, this pink is not very visible. If I'm not writing big enough or in weird colors, just stop me, okay? So E0 is 1 square root 1 minus P 0, 0. And E1 is 0 square root of P 0, 0. This is a weird cross operator set. Why is it weird? First of all, there's no identity here. If you have amplitude damping, there is no such thing as nothing happening. Even if you don't get a quantum jump, this is a quantum jump that gives you a click from 1 to 0. Even if you don't get the click, if you didn't emit the energy, well, then you apply more and more weight to you being in the ground state. So you get information, and therefore, the cross operator corresponding to the no click event is not the identity. And in particular, note that these are not Pauli operators either. You can't write it in a Pauli form. But again, it doesn't matter because you can decompose it into Paulis. Did that answer your question? More questions? Yes.
so when you define that initially that error operator, so it was like unitary operator sandwich between the initial and final state of environment. So now there is no such like the what unitary operator we applied. So these errors are independent of that, or like
I'm not sure I understood the question.
so initially when you wrote the error operator,
Yes.
so that you written as like some expression values under the unitary. I mean, the unitary operator total which acts on the system
Yes.
plus environment,
Yes.
and that is sandwiched between the initial state and final state of the environment.
Yes.
So now you're writing, let's say here the error operator as some only the Pauli matrices. So
Yes, this is the operator just on the system, and it comes from a unitary on the environment, but you're forgetting about the environment, and then you get this kind of stuff.
So any evolution of the, it is independent of the any evolution U. I mean,
No, the U will determine what kind of cross operator you get.
okay.
It's the U that tells you what EK is. I want to talk about two more error channels that are important. E naught is square root 1 minus P identity. So sometimes nothing happens, the environment doesn't measure. Sometimes it collapses you to the ground state, 1, 0, 0, 0. Again, not unitary. And sometimes it collapses you to the excited state. This equals actually 0, 0. This equals 1, 1. The thing is, you can rewrite these cross operators. Let's see how. So rho goes to 1 minus P identity plus P times 0, 0, rho 0, 0 plus 1, 1, rho 1, 1. So far, so good. But you can rewrite this. Okay, good. This is 0, 0, rho 0, 0 plus 1, 1, rho 1, 1. And you can rewrite 1, 1 as identity minus z over 2. And you can rewrite 0, 0 as identity plus z over 2. You rearrange the terms, and lo and behold, what you get is 1 minus P over 2 I rho I plus P over 2 Z rho Z. Does anyone have anything to say about this? I'm patient. It is the phase flip channel. Okay? So you start with a different story. The environment is something entirely different to your system, and yet effectively on the system, it looks identical to the phase flip channel. The intuition is that both these channels, they destroy the phase. If you measure a superposition, you destroy the coherent superposition, you destroy the phase. And if you apply a random Z flip, you also destroy the phase. So it shouldn't be too surprising. And a bit more from a mathematical point of view, it comes from the fact, and this is related to a question, it matters what unitary you apply to the system and to the environment, but it doesn't matter what the environment do with the information afterwards. The environment can apply a different unitary operation W and then measure, or not measure, doesn't matter. This will give you different cross operators here, but the channel will be the same channel effectively. This is called freedom or unitary freedom in the operator sum representation. Yeah, it's true. I haven't discussed non-Markovian dynamics here. I could. I presume you could also describe it in this framework. So these time-dependent fluctuations can be recast in the operator sum representation. But yeah, this is maybe, this opens a whole can of worms that I don't want to get into. And I want to finish with the depolarizing channel. This is what maybe the most famous and most infuriating to experimentalists channel. It's the most famous because this is what is used to model quantum error correction codes. It's a very, you can prove a lot of things analytically using the depolarizing channel. As an experimentalist, this thing doesn't exist in real life. But it's a very useful tool. And what this tells you is your density matrix, well, either it stays the same, or with the probability P, you apply either Pauli operation with an equal probability. So I rho x, I rho I plus x rho x plus y rho y plus z rho z. And your first homework will be to prove that this thing here, you can write it as a density matrix, chi. And this chi is equal to I over 2. It's the identity density matrix. What is this density matrix? It's a fully mixed state. It's just the origin of the Bloch sphere. Not surprisingly, so you take a density matrix, some vector on the Bloch sphere, and then you rotate it along an arbitrary direction. On average, you're left with the original state. Sorry, with the fully mixed state. You can prove it by looking at the average x, so the expectation value of x, y, and z of chi. And be careful because I made this very smart choice of taking y to be non-emission. So y square is minus the identity. I wasted 15 minutes yesterday trying to understand what went wrong. Good. And so this is equivalent to saying that the depolarizing channel keeps you the same with the probability 1 minus p, and with the probability p, you go to the fully mixed state. It erases all information. Okay, this finalizes my preliminary section. If there's any questions, maybe now is a good time. Yes. There's always some physics, there is always structure to noise. And as Prabha mentioned, you can exploit the noise to improve your error correction. And this is kind of a worst case scenario where you erase all your information.
So I have a question. So I didn't get the exact statement about the unitary freedom in the operator sum representation. So is it that if you have a channel and upon unitary operations, there is an equivalent channel with different Krauss operators, or is there a unitary equivalence between the Krauss operators which give you the same
You
kind
can map a set of Krauss operators to another set of Krauss operators using some unitary transformation. So they are an equivalent channel, but they're different decomposition into a different set of Krauss operators.
Can you repeat the argument? Why did you say that the measurement channel is a kind of a special case of the phase flip?
Yes. If you start with the superposition 0 plus 1 and you measure it, what you end up with is a fully mixed state. You have 0 with 50% probability and 1 with 50% probability. So it's an average of this state and this state, which you here. If you have a phase flip channel and you start with 0 plus 1, then with a 50% probability, it leaves you here. With a 50% probability, it rotates you by pi. And you have a 50-50% probability of these two, which also gives you the origin. They both destroy the phase. That's the intuition. It maybe takes some time to appreciate, so mull over it during lunch. More questions? All right. So let's start with the basics of quantum error correction. Now that we understand the errors. And the essence of quantum error correction is to use redundancy to protect quantum information. This is also the essence of classical error correction, so it shouldn't surprise you. Or to protect quantum information. And you do it by taking a certain message, number of qubits that you want to send. Suppose you want to send k qubits. You map them into a new Hilbert space that has more qubits in them. Let's call this number n. This is the number of physical qubits. And n is bigger than k here. And finally, well, this is what you send through your noisy channel, now that it's redundantly encoded. And at the end, you decode it, and you translate it back to the message, which will hopefully be uncorrupted. We have three parts to an error correction sequence. I'm not talking about computation in this talk or in the next ones, just about maintaining or storing information. This is the encoding step. This is the noise channel or error channel. And this is the decoding. The noise channel in real life, it can be just storage. So it's a channel over time, or it can be communication, 5G or Wi-Fi, and then it's transmission over spatial degrees of freedom. It doesn't matter. The theory of quantum error correction is oblivious to this fact. And what we want in quantum error correction is to maintain the quantum information. And so the composition of these channels, each one of these is a channel which has a set of cross operators, and their composition should give you I should stick to my choice of colors, shouldn't I? We want epsilon and d to be equal to the identity. So when it acts on rho, it should give me back something with a high probability that equals rho. This is the goal of error correction. A classical picture to better appreciate what I've done here is you start with some set of logical bits. This is the information you want to send, 0, 0, 0, 1, 1, 0, and 1, 1. But there's noise along the way. And so you encode it in something much bigger. These are now your logical code words. That's what they're called. These are the legitimate messages. But there are a lot of states in between, because you have a lot of physical bits. This is going to take me a while, but you get the idea. Now, to corrupt the information, you need to act with a lot more errors to go from one to another. And so the smallest number of steps that you have to take to go from one logical code word to another, that's called the distance, d. A very important parameter in quantum error correction. And for any error that is smaller than d, excuse me, d over 2, you can correct that error. Why? You can just draw a circle around each logical code word, a circle of size d over 2. And if you find yourself in here after the transmission of the message, well, this physical state here belongs to this code word. Let's write this down. So the common nomenclature in the field is to call the number of logical qubits.
Sorry, I have a question.
Yes.
So I didn't understand the picture you are drawing here. So it's like what we can you just
What I try to draw here is here you have a space that has 4 possible states. And then any error will map you from one type of message to another. You don't want this. You want to use redundancy, which means you're going to a space with many more states, physical states. And then you spread out your code words in the space so that it takes a lot more effort to go from one logical code word to another. So there's a thing called the Hamming weight. This is for classical codes.
Sorry, I have a slightly follow-up question. So on the left, actually, here. So here, on this side. Yes. So when you say space, you're not talking about the real locations of the qubits. You're talking about the state space.
Yes, or in quantum error correction, the Hilbert space. Okay. So it's a 2 to the n. This is what I tried to draw here. You go from a 2 to the k dimensional Hilbert space to a 2 to the n dimensional Hilbert space. We'll see many examples, so I hope that this will be clarified soon. So we say we have n physical qubits. And we say we have k logical qubits. Or in the classical case, bits, of course. And D is the smallest operation. Excuse me, it's a Hamming weight. Hamming weight is the number of elements that are not 0. I'll explain soon. So it's a Hamming weight of the smallest operation that brings you from some code words X to another code word Y for any X and Y. X to Y, and of course, X cannot equal Y, and both X and Y have to belong to the code space. The code space is just a space of the set of code words. I mean bits here, yes. Yes, yes, thank you. But these concepts will generalize very naturally into qubits. So you can think about it as qubits, yes. Yes. So the code space, let's give an example. And then maybe we can continue with the question. Example. The code space can be 0, 0, 0, 0. I have 4 physical bits, 1, 1, 1, 1, 1, 1, 0, 0, and 0, 0, 1, 1. So there are 4 physical bits, n equals 4. How many logical bits are there? 2. 2 logical bits. I have 4 code words, so they encode 2 bits of information. This could be my logical 0, 0. This could be my logical 0, 1, etc. Okay equals 2. What is the distance? So the Hamming weight is the number of ones in a string of bits. What is the distance here? 2. Why 2? Because, yes, to go from this one to this one, I need to flip 2 bits, namely these 2. This is classical. I'm sorry, I'm making a bit of a mishmash. But this is classical, but it will translate very naturally to qubits. And I should have made that distinction. In qubits, the distance is the smallest number of Pauli operators that you have to apply to go from one state to another. So it's a trivial generalization. Is this clear, this example? Distance is 2.
Does the D have to be same for like all the points in the space? Like,
No.
do they have to be uniformly distant?
No, D is the smallest operator.
Among them,
So
which
it's the one that promises you, that if you have fewer than D over 2 errors, that you can then recover the information.
Okay, thanks.
Let me write that down. We call this thing an NKD code. N physical qubits, K logical qubits, and the distance D. And again, the same jargon applies to quantum error correcting codes. We call this an NKD code. So it's any classical code that can detect how many. So what is the Hamming weight of the number of errors that can be detected? How many errors can you detect when you have this kind of code? I'm not going to walk all over there. What is the largest number of errors that you for sure can detect? Someone from the back rungs here. How much? Yeah. Well, 1. Did I say smallest? What is the biggest number of errors that you can for sure detect? For some NKD, if D is the minimal number of bit flips, D minus 1. If I have D minus 1 bit flips, I can never go from a green point, from a logical bit, to another logical bit. So I can always detect that I'm not in the right, in the code space. So we can detect D minus 1 errors. But we can also only correct D minus 1 over 2. To correct, I need to go back to the correct code space, code word, and therefore I need to know in which circle I am. You need to find the closest logical code word to where you are. And I sense I'm losing a part of the audience, so I'll take some questions now. Yes, Yuval. Yes.
So if I take one error, I know it was an error and I know how to go back. So what was the code well?
No. So suppose you have one, okay. But you asked the question, I have to answer. That's how it works. Suppose you start with 0, 0, 0, 0. And now you have one bit flip. And you go to this. Now you can detect this error because it doesn't equal any of the original code words. D minus 1 is 1, so you can detect any single bit flip. But D minus 1 over 2 is 0 if you floor. So you cannot correct this. Why can you not correct this? Because you don't know if it came from 0, 0, 0, 0, or if it came from this one. We have ambiguity, so you cannot correct this error. Yes?
What is the code space and what is the error space? So what are you taking as a code space?
In this example, the code space are these 4 logical code words.
What is the error?
Anything that is not in the code space is an error space, is in the error space.
Then we are not looking for error and outside. If I have an error which takes me outside, then I will say that's an error. Get back to it.
No, there are no degenerate codes in classical error correction. So I could write the full space, all 16 possible combinations of bits here. So it's, yeah, 16. This is the code space, and all the 12 that are not in the code space, these are errors. For example, 1000 was not in the code space, it's an error space. I will give many examples of that, so it should become clearer as we move on. I want to maybe a question from the students.
I think we should now for a big question.
Yes. Yes. Okay. Question from the second row. On both? Yes, it will depend on N and K, but more generally on the type of NK code. So you can have 2 codes with the same N and the same K, yet one will have a larger distance than the other. And by the way, the rate of
I have one doubt.
let me just finish the sentence.
Yeah,
the
sure.
rate of the code, it's a very important concept. This equals K over N. Okay, this is the overhead. This is the 1/1000 that we saw in the beginning. How many physical qubits do you need for 1 logical qubits? And so this is something that we really want to optimize when designing quantum error correcting codes. Yes.
Yeah, so all these discussions is for classical error correction. So here we are assuming only bit flip, but when we go quantum, we'll assume other errors also. So
Thank you. This is a perfect question because now I'm moving on to quantum errors, to quantum error correction, which is why, after all, why we're here. And so you'll get your questions answered. Yes. Yes, so D tells you how many errors you can detect or correct. There are subtleties. For example, D tells you what is the what number of errors can I for sure correct. But sometimes you don't want to be absolutely certain. You want to be 99.9999% certain. And so N and K have come in when you ask questions about, am I able to correct typical errors? And we'll get to that in the coming lectures. So let's go to the quantum case. And we'll start with a simple qubit, alpha 0 plus beta 1. The code space is trivial here. There's only N equals 1 here, and K equals also 1. It'll help us get our terminology straight. The code space is the span of 0 and 1. And I run into a problem here, because if I have a bit flip, I go to alpha 1 plus beta 0. What's the problem here? Can I detect this error? I cannot. Why? Because it's an element of the code space. It's inside the span of 0 and 1, so I cannot detect it. Similarly, if I have a Z error, I get alpha 0 minus beta 1. And by the same token, I cannot detect this error because it belongs to the span of 0 and 1. So I cannot detect it. It's clear that to be able to detect errors, we need to go to a larger N. Now, it would be okay if you were part of the code space, but if it acted trivially. If you have an error that keeps you in the code space, but it doesn't do anything, you're fine. But here, that's not the case. This is a logical operation. This is an important distinction. So let's focus on the bit flip channel for now. And let's go to 2 qubits. You know, a few years before India successfully put the Chandrayaan mission on the moon, there used to be a Google X competition for the first private commercial entity that's maybe not commercial, private entity that puts a spacecraft on the moon. And there was an Israeli company, there is an Israeli company called Space.il that attempted this maybe 5 years back. And they reached the moon, amazingly, but a bit harder. The landing was a bit harder than with the Chandrayaan, so it exploded into pieces. And why am I telling you this? Because these guys probably came to my class and they learned about error correction. And to succeed next time, which hopefully will be next year or in 2 years, they're going to send 2 probes to the moon. Okay? So this is what we're going to do next. If they were to come to my lecture number 3, they would have sent 3. And then it would for sure work. So with 2 qubits, let's call our code C equals span 0, 0, 1, 1. These are my 2 code words. And what is K here? 1. It's 1 bit that I can encode, 1 qubit. Did I not say it? A code is a 2-dimensional subspace, or a 2 to the k dimensional subspace of a 2 to the n dimensional Hilbert space. This is what a code is. Thank you. And any state within the code space can be written as alpha 0, 0 plus beta 1, 1. Note that Guru Prasad talked about the no cloning theorem. This does not violate the no cloning theorem. We're not taking a qubit here and copying it. That would give you alpha 0 plus beta 1, tensor product alpha 0 plus beta 1, which is not equal to this. Now let's apply a bit flip to this state and see what we get. So xi, psi, this equals alpha 1, 0 plus beta 0, 1. Can I detect this error? Can I detect a bit flip on qubit number 1? Yes, I can. Why? Well, because I'm not in the code space anymore. This is not part of the span of 0, 0, and 0, 1. I can call this the error space, like you suggested. Let me call it CXI. Similarly, so I can detect this error. Similarly, IX, I can also detect. Now I'm applying a bit flip on qubit number 2. This also is not an element of the code space. And so 1 qubit bit flip is detectable. Now, can I correct these bit flip errors? No, I cannot. Why is that? You don't know where it came from. Yes, it's true. And why do you not know where it came from? This space and this space are identical. CXI and CIX are the same space. They're the span of 0, 1, and 1, 0. And so there is no way to know where you came from. That doesn't mean you cannot correct, because maybe it's not a problem. Maybe if I got a bit flip on the first qubit and I correct it by applying a bit flip on the second qubit. Maybe this is a trivial operation on the code space. Let's see. Suppose I have IX on psi, and I don't know if it was IX or XY, XI. So I correct it with the wrong one. And now I get XX on psi, which equals alpha 1, 1 plus beta 0, 0. Well, the problem is this does not equal psi. I have lost my information. I have applied a logical bit flip on my original qubit. And so this error correction didn't work. So remember that it's okay if two errors bring you to the same codes, to the same error space. This is called degeneracy. But you can only correct it if it doesn't matter which one you apply. And here it does matter. That's clear. Yes, let me just write it down. So
Question?
one qubit bit flip is not error correctable. Yes.
One thing that I'm not sure has been explained, you said you can detect it and then correct it or not. Yeah? In the classical case, detecting is inconsequential. You just do it. But in the quantum case, detecting means interacting with the state and hence changing it. So even before we start correcting something, we maybe should discuss the consequences of detecting.
We should discuss
The consequences of detecting.
Yes, yes.
I mean,
So we're going to have the whole next lecture is going to be about how do you actually do this. But actually, this is a good place to ask. So how do you detect that you're not in the code space? What do you do to your qubits? What you cannot do is measure your qubits. This is not allowed. If I now ask the question, is qubit number 1, what's its state? I collapse my superposition and my information is gone forever. So what do I have to do? Measure? Yes, I have to measure a global property of both qubits. For example, I have to correct the parity of these two qubits. If the parity is odd, I know I'm in this space without collapsing the superposition. If the parity is even, I know I'm in the code space. We'll talk a lot about this in the next lecture. So we use parity measurement or check operators to detect these errors. And how am I with time? Do I have 10 more minutes? Great. Great. Okay. So we have an error detection code, but not an error correction code. If we want an error correction code, we need to go, as I said, to 3 qubits. Now the code is the span of 0, 0, 0 plus 1, 1, not plus, comma, 1, 1, 1. And in this case, let's draw the entire phase space. That I draw this picture with many dots. You can now actually draw it for this case. So this is my logical 0, and this is my logical 1. I think you get the idea. I'm not going to do the other ones. Now, if I start, for example, in 0, 0, 0, and I have a bit flip, I go to its neighbors. And now I can detect that I'm not in the original space, but I can also correct. Why? Because this point here, this state, is going to be closer to 0, 0, 0, and it's going to be further from 1, 1, 1. Okay, to go to 111, I need to apply 2 bit flips. To go to 000, I need to apply only 1. And so in this case, I will be able to correct. So if we draw it as a picture of subspaces, the code space C, it was the span of 0001111. If I have an error on the first qubit, a bit flip error on the first qubit, I go to the error space, which is the span of 100 and 011. This is orthogonal to the original code space. If I have a bit flip on the second error, on the second qubit, I go to 010-101. Notice that this is orthogonal to the original code space, but it's also orthogonal to the bit flip on the first qubit. And finally, I have here the span of 001-110. So I have a set of completely orthogonal error spaces. And so I can both detect an error and correct it by just applying the inverse operation. And this is what quantum error correction is. Quantum error correction is collapsing yourself to one of these 4 spaces, 2-dimensional subspaces, deciding in which of these you are, and then applying the correction. And you have to do it without collapsing you within the code space. So you have to ask, in quantum computing or quantum information, it's very important which questions you ask, which measurements you make. And the only measurement you're allowed to make is, in which one of these 4 partitions am I? We say that yes. And next week, tomorrow we'll talk about stabilizer codes, which have a much more efficient representation. So suppose I have a bit flip on qubit number 3. And suppose it's not a bit flip, it's a coherent rotation that gives me a superposition of a state that lies in both of these. So it's in a product with these 2 subspaces is not equal to 0. What I do is now I measure the parity. I ask, are the two last qubits the same or are they different? And I have to ask the same about other qubits. And now I know whether I'm in this one or in this one. And of course, at this point, the superposition has collapsed. Okay, so I will be definitely in here or in here. And I forget about any phase that was in there in this operation. And so, for example, sometimes people ask, okay, you can correct against errors, but what if my gate that I apply is a little bit off? It doesn't matter. It's a superposition of polys, and when I measure, when I detect if there's an error, I sever the ties between these options. Yes, I lose the information about the phase, and I lose information about what was the probability that this error happened or not. It's just that I.
But it's not probability conserving.
Suppose I go to this, I start in 0, 0, 0, and now I go to the state 0, 0, 0 plus epsilon. Nothing will be normalized in my talks, so don't ask me about it. And I go to 0, 0, 1, but I have this epsilon superposition. When I measure, is this qubit equal to this qubit? I don't gain information about whether I'm here or here. But what happens is I collapse myself. With a 1 minus epsilon probability, I go to 0, 0, 0. And with an epsilon squared probability, I will go to 0, 0, 1. Yes, the probability of seeing an error will be related to the coefficient in this unitary operation. More questions from the audience? Yes.
So So in the 2 qubit case, we saw that the 2 error space are that are completely overlap. So is it equal to, if we have some partial overlap, let's say they shared some basis, so is it still we can correct it, or we require full overlap?
If there is a partial overlap between the spaces, then we have a problem, because sometimes we can be confused. And so it will only be correctable if going back to the original state gives you a trivial operation. We will get to that, I hope.
So I have one more question. So
yes.
So we will take the code space always so that we have d equal to maximum, because that rate we define by only k by n. So here, let's say we can take this C to be span of 0, 0, 0, and let's say 0, 1, 1, not 1, 1, 1. So we require that D to be, we'll take the code space always so that the D is maximum. I mean,
I'm not sure I understood the question, but so here in this code, this is a quantum code we write with double brackets. This is a 3 physical qubits, 1 logical qubit, and D equals 3. Or rather dx, we're talking only about bit slips for now. Dx equals 3. You have to have at least a distance of 3 to be able to correct errors. There is one more question, and then we'll move on. Yes.
Yeah, so I wanted, so it's a 2-part question. So as you pointed out that—
Decide the most important part.
No, both are short. As you pointed out that once you measure, you collapse in one of the state.
Yes.
So your goal is to just go back to the code space, right? In the correction term.
Yes.
However, there are many elements in the code space. We are not concerned about distinguishing between them, right?
It's not only that we're not concerned, we cannot touch them. We will get to that. Good. Okay. Now, does this code correct phase flip errors? The answer is no. Let's see why. As you might suspect, if I apply a phase flip, a Z operation on one of the qubits, for example, ZII on alpha 00 plus beta 111, well, then I go to alpha 00 minus beta 111, which again is an element of my code space. And so I cannot correct phase flip errors, even not a single one. Let's do a calculation. This was mentioned in one of the talks last week. What is the smallest number of physical qubits that can allow quantum error correction for all single qubit errors? So what is minimal? What is the minimal n? To be able to correct for a single logical qubit any single qubit error. And we can do it using a simple counting argument, which will give us what's called the Hamming bound. How many errors, if I have n physical qubits, can there be? How many errors do I have from the back rows? If I have n physical qubits, 3n. Okay, I can have x, y, or z on any one of these physical qubits, or I could have no error. So this is the total number of possible events that I could have. And for each one of those, single errors, yes. Yes, yes. This is, it generalizes to more errors, but I'm gonna, for the interest of sake of time, I'm gonna stick to single qubit errors. And for each one of these errors, I need a 2-dimensional subspace. So I need 2 states per event. And I need to house all of these states within n qubits. How many states do I have with n qubits? 2 to the n. So I get, if you do the math, n is smaller or equal than 5. And it turns out that there is a code that actually is a 5-qubit code. It's called the 5-qubit code. and it corrects any single qubit error, including phase flips, including bit flips and phase flips. Excuse me? Oh, thank you. Now, this assumes that all of these spaces are non-overlapping. It assumes what's called a non-degenerate code. But there is a different bound called the singleton bound that shows that it cannot be smaller than 5 anyways. If you have overlapping spaces, you can pack more information within your Hilbert space, so it could be more efficient. Yes. Okay. So in the next lecture, I would like to talk about, I'll take a few minutes to talk about the first quantum error correcting code that corrected both bit flip and phase flip errors. And this is not a 5-qubit code, which is complicated. Rather, it's called Shor's code. It's the same Shor from the algorithm. He was annoyed that people said his algorithm couldn't be executed. So he invented an error correcting code. And then people said, oh, but your error correcting code won't work because your error correction procedure is not perfect. So he invented fault tolerance. And now I think he's satisfied. So we'll talk a bit about Shor's code in the next lecture before delving into stabilizer codes. Questions?
Yeah, a quick one. This counting 3n, I mean, you said x, y, and z, but what about linear combinations? I mean, x plus c, they are counted.
Yes. So remember that in the beginning, we talked about digitization of errors. We can write any error as a superposition of x, y's, and z's. And so it's sufficient to detect only x, y, and z, even though your errors could be superpositions of those. Again, these superpositions will be collapsed to the basis that I choose for my error correction. It doesn't have to be x, y, z. More questions?
Well, is it possible to know what kind of errors are actually occurring in the system? For example, I mean, here we are only discussing single bit flips or single phase flips, but you can like arrive at the same state by 2-bit flips. So do you know, like, is there a way to know which error is occurring and leading to the state that we are at?
One could spend a whole semester on talking about errors that happen in physical systems and characterizing those. The answer is you have many different kinds of error structures. And these errors can be single qubits. They can be correlated errors where these errors spread. It's a whole world, and it's a very important subject. But we're not going to go into that. Right?
But then is it true that just correcting single qubit errors is, I'm online actually if you're looking for me. Okay, is it true that just correcting single qubits can correct the entire system? Or?
Yes, so if you can correct, well, if you have an independent error channel, so the errors affect every qubit individually, then this sequence will work. This, error correction will work. If you have, for example, correlated errors and these errors spread very rapidly, then this framework will not hold anymore. So very often we assume that the errors are independent on each qubit, or at least that the correlation decays very quickly.
Okay, thank you.
Yeah, so in that 3-qubit case, when you applied that phase flip, so it remains in the same code space because like we can detect it's the minor beta sign change. So what extra happens in the 5-qubit case so that it goes out of that C space so that we can detect?
Yes. So what is it that allows you to detect phase errors? That we will see when we talk about the 9-qubit code in the next lecture. But the answer is you need entanglement. Okay, you need your code words to not be 0, 0, and 1, 1 because a phase just puts a minus here. You need the phase to bring you to an orthogonal. You need the phase flip to bring you to an orthogonal state. For that, you need entanglement in your system, as we're going to see.
So for that entanglement, we require the 5-bit. I mean, in the using
Yeah, so
3-bit.
the 5-qubit code, every code word, no matter which code word, will be in entangled state. Yes.
Can you just walk over the counting argument you just did there? I didn't get that.
Yes. I actually want to use this. If you count the number of qubits, you have n qubits, you then count the number of errors you can have. So if you have 3 qubits, you could have x on qubit number 1, x on qubit number 2, x on qubit number 3. If you allow for y and z errors, you would need more arrows. You would need 3n arrows. But then you have the original code space. So you have 3n plus 1 of these 2-dimensional subspaces. These all have to fit into the cube, which is 2 to the power of n points. And this is the inequality I drew here. Is there enough space in my Hilbert space to house all of these orthogonal subspaces? And the answer is, for 1 qubit, I need at least 5. If you only want bit flips, then it's 1 plus n, not 1 plus 3n. And then you will get n is bigger than 3. Bigger or equal.
Maybe one last question.
By the way, you have my email, and I will stay around so you can ask me many more questions.
Much better to have
Just not during lunch, because I'm very busy eating. Okay?
Yeah. So to define the errors, probably this is related to earlier question. So to define the error space, so you have the density matrix. Probably you can impose some conditions on the initial density matrix, and then you have the completely positive trace preserving maps.
Yes.
So it's the action of this on this should define the error space. So how constraining is this, or how constraining can you make this so that you can get a well-defined error space, or is it completely uncontrolled?
I'm not sure I understood the question, but there is a theorem which I'm not sure we're going to get to. It's called the Knill-Laflamme theorem, and it tells you, given a process epsilon, which set of cross operators can be correctable in principle without even talking about the code. Just in principle, is this set of cross operators correctable? So there has to be some structure for this to be possible. We will talk about this.
All right, very good. Let's thank Serge for an excellent talk.
Thank you.